There was one thing, because I know Rich is raising his hands back there saying, not again, you missed it. When Richard was unable to do his demo earlier, Rich Green pointed out conveniently that within each of your bags there's a USB, and on that USB is Demo Bench that we talked about. So you should have everything on that USB drive you need: videos, white papers, the distribution of Corda, and Demo Bench, which allows you to go run the demos yourself. So, and Rich has kindly offered to do a webcast to let everybody, walk everybody through that demo so you can see how to run it. Thanks, Rich.
Okay. All right. Can you hear me? Super duper. So this talk is about privacy techniques. We heard a bit about SGX this morning, so we're only going to touch on that briefly, and we're also going to discuss the competing strategy that some of other platforms in the DLT space use, which is zero-knowledge proofs. Now, we haven't really talked much about that up until now because we've been talking about the things we are doing versus the things we are not doing. But of course, it is a reasonable thing to ask what has led to this strategy, what was the thinking that went into it, and also, of course, what are these zero-knowledge proof things. My colleague here, Kostas, who's one of our 3 cryptographers, will be assisting with an explanation of how zero-knowledge proofs work and the basics of the technology. And then I'll be discussing a bit about the comparisons between SGX and ZKP. So that's what this talk is about. Now, privacy is one of those, you know, what we are trying to do with distributed ledgers is a paradox, right? We're trying to share data, but also not share data. And that is not a very easy thing to design. You know, you want to share it because people need to be confident that the transactions are valid, that the ledger has integrity. But you also don't want to share it because you don't really want them to learn anything but that integrity exists. You don't want them to learn why it exists, just that the ledger is correct. So there are lots of different techniques that can be used to do this. So there's, you know, there's the advanced cryptography. There's things like zero-knowledge proofs and ring signatures and homomorphic encryption and multi-party computation. There's also secure enclaves with SGX, which we heard about from Simon this morning. There's also techniques like what Bitcoin pioneered. Simple things like key randomization. You just change the identities in transactions to be random and anonymous. And then, you, of course, you want a way of linking them back to a legal identity. So this is a feature that we call confidential identities to distinguish it from the Bitcoin thing, which is just randomized keys. Confidential identities automatically anonymizes and de-anonymizes identities at the right time. That will ship in version 1.0. So our privacy story is actually more encompassing than just SGX. We have other things, too. For example, our transactions are structured in what's called a Merkle tree. Those of you who have studied Bitcoin or Ethereum will know this data structure. That allows you to reveal bits of a transaction without the rest. And then there's a whole bunch of other things as well that we can add on top. On the other hand, we also have, you know, individual features of any given scheme. For example, if an algorithm becomes weak, how quickly and easily can we switch it out for a newer algorithm? This is especially relevant with the impending quantum apocalypse, which Kostas will discuss as well a little bit. You know, how do we deal with random number generation, things like that? Does a PKI fit into this, and so on? So there's a ton of different technologies, all of which need to be considered, evaluated, designed, integrated, and possibly deployed. And a big part of the work we do as part of the platform on your behalf as app developers is figure a way through this maze without getting eaten by one of these monsters that's along the way. And there are quite a few. All right, so let's do a quick recap. So we, you know, we announced we're working with SGX a bit earlier this year. There is, you know, well, so silicon from Skylake Plus, which Intel Skylake chips started coming out at the end of 2015, have SGX. It has the features which Simon covered this morning, the encrypted memory. You can seal off your software, and then you can prove to other people you've done it. And this is a pretty good fit, turns out, for distributed ledger technology. And many other things, too, not just DLT. It's very flexible technology. So that's the route that we're going, but of course not everyone is going that route. So there we go. To make this easy for people, you know, you don't want to write your smart contracts in C because you'll get it wrong. I guarantee you'll get it wrong. Even if you think you know C, you don't. And so, you know, we have a JVM that gives you memory management and so on. That runs inside the enclave, and this is being integrated into Corda at the moment. And what this gives us is an encrypted global ledger. So we get to have our cake and eat it. We can share data, yet not share it, which is what we want. Now, there's an intro-level talk. This morning's talk was very in-depth. It was very technical. It was for those of you who really like the meat on the bones. There's a talk available on our Vimeo channel, which is designed to be understandable by people in the business, your management chain, and so on. It's a high-level overview of what this whole thing is about, what we've done, in such a way that you can understand it without much technical background. It doesn't discuss page table bits and things like that. So you can go watch that video. That talk has like cool videos of robots in Intel's factories and things, so it's worth checking out just for that. But this is not a repeat of that talk, right? So that's enough for me on SGX. You've heard a bit about it today. You can hear more if you go online. What I want to talk about now is why we're doing this and not doing what, for example, Ethereum is chasing, which is the zero-knowledge proof route. OK, so before we can discuss a comparison, you have to know what we're talking about. So I'm going to hand off to Kostas, who is going to give us a tutorial on zero-knowledge proofs.
So everyone would have heard of zero-knowledge proofs these days. It's one of the most amazing technologies happening. And in fact, the concept was proposed back in 1985. So there have been 30 years, almost 30 years, without a solution, a practical solution, actually. And for those that don't understand what's the meaning behind zero-knowledge proof is we have an entity, a prover, that wants to ensure that an information that wants to prove to a verifier that the statement is true without revealing anything else. So I will just get to some examples so you can easily understand the concept. It's OK. So imagine that back before even TLS is applied or SSL, we had to send, for example, a password in the server, and the server had full knowledge of this password. So the actual concept was to verify our identity. But in practice, what we did is we revealed our secret as well. So there was something required to change this process. Eventually, we've used another layer, TLS, that we sent a hashed password, then someone can break the password. Imagine if there was somehow a mechanism, a design, that could protect you from the server knowing the private key. And if the server infrastructure is compromised in the future, the secret is still secret. This is very important. And it's one of the concepts of zero-knowledge proof. It's that I can prove ownership, that I own a private key or something or a password without revealing this information. Then let's go to something, let's go to some games. For example, the treasure hunt game, you want to reveal that you know the information of where something is hidden without stating or give some information, even a small information of where this location is based. And all of these examples, for example, Sudoku. Do you know Sudoku? I mean, it's just a simple puzzle game. You can actually, however, prove that you know a solution to this game without actually giving the solution to the reader. And there are more examples. There are e-voting. There is sealed bid auctions. Imagine that we can now prove who won in an auction without revealing all of the bids, or any of the bids. Or the bidder itself can actually prove that, hey, I put my bid, it's already there, but I don't want to reveal my bid to you. So there are so many problems that zero-knowledge proof can actually solve. I will explain later why it's not always the case or why it's not practical sometimes. But let's go to our world, to the finance world. Imagine we have to prove you are a part of a group without revealing your identity. Imagine, for example, ring signatures, or that we want to prove that in Corda, for example, someone signs a transaction. We don't want to know who is this someone, but we want to know that it's a member of our group, which is very important to actually find the solution against some denial of service attacks or some other attacks that can happen. And what's more important is we can now prove that we can make a transaction without knowing the actual value we're transacting with. We just know that I just had at least the amount required for this transaction in my account. These are all examples of zero-knowledge proof, and there are so many others that, any other problems that we can reduct into an NP problem. The issue with zero-knowledge proofs is that there are so many definitions. Actually, there are sound proofs or zero-knowledge proofs. There is a zero-knowledge proof of knowledge, like the example we said before with the ownership. I can prove that I hold the key, but this is the only thing that I'm proving. There is a witness indistinguishability, which means I'm not proving something as a true or false, but I'm stating that you don't know which of the keys I used. Let's say I had 4 keys, and I'm not telling you which key was used for this transaction. And there is also the ring signature, as we said before, that we cannot determine which of the group members was actually the signer of a particular message. There is the multi-party computation. Imagine there is a paper now stating that zero-knowledge proof can actually be a 2-party computation where only one of the parties has an input on it. So again, we compute something secretly. Only one member puts some input on this, let's say, proof. Then we have a zero-knowledge proof again. And let's say homomorphic signature for those who are familiar with crypto stuff. Let's say we have 2 signatures, one signing the amount X, another signing the amount Y. Then we can compute by the homomorphic feature of this signature that by combining this signature, we can prove, for example, an operation between these two values. Imagine, for example, a donation scheme. Some people are donating money. They don't want to actually reveal the amount they donated, but we can have the full donated amount at the very end, and anyone can prove it. At this stage, I will make an experiment with Mike. This is the first time we try together. We will need some balls. Mike, I need you to the stage. OK, it's juggling.
Well,
no.
You said we weren't going to be juggling.
No.
I trusted you.
I think some of you are familiar with the Alibaba cave, where is one of the most famous problems that you can prove how zero-knowledge proof works. Now we'll make the shortest ever experiment about zero-knowledge proofs. It just requires 2 balls, and I'll explain why. Yes, orange and red is good. Yeah. Let's say I'm blind. Before putting this, I will explain the rules because I can see how it works. Where the concept of this experiment is to prove to you that even though I'm blind, Mike can convince me that these balls have different colors. This is difficult, OK? I mean, I'm blind. How can I say that these balls are different in color? So I will put this. OK.
I'm colorblind. Does that matter?
Are you colorblind?
We didn't practice this beforehand.
OK.
Okay.
Can you see the difference between these balls?
Yes.
OK. Give me the balls. What we're going to do now is that I will. Mike just told me, hey man, these balls are different. I'm touching them, but I'm blind. I can't see if they are different. I don't believe you, Mike. So Mike says, OK, let's make a challenge. So what I'm doing now is I will put a ball in front of Mike, and in the next stage, I will ask him if I did something, if this ball changed. So we start with this. You don't have to say nothing.
Okay.
And on the next change, you will just say it changed or it's the same. Okay?
It's the same.
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 It's different.
It's different.
It's the same.
It's the same. So if I follow this, I will put this out now. If I will follow this process, for example, 128 times, it's highly unlikely that Mike could find out that these balls are different if they were not different. But I don't know the color. I don't know which one is orange and which one is red. But somehow he convinced me. The only statement was these balls are different without revealing which ball is red and which ball is orange. So this is how interactive proofs work. And if you understand this concept, then you will get the meaning behind zero-knowledge proofs. This is the shortest example ever, and you just need 2 balls to do it. I can even do it with more balls. For example, there are some properties in zero-knowledge proofs, especially the faster ones, that say that while you are making the problem more complex, then the proof should be bigger or smaller. Imagine that I had 4 balls, and Mike had to convince me that all of the 4 balls were different. Either I had to do it one by one 6 times. I think the combinations between 4 balls are 6. Or we can use all the 4 balls and have a more, let's say, more complex transaction between us, but less iterations. So this is one of the best examples of understanding. You can even explain to a child. Now it's very easy. And I will go to something, to something which is related to the actual practical example of zero-knowledge proofs. We can't do this thing by exchanging information in real DLTs and blockchains. It's too difficult and it takes time. However, you can easily think of a way how to avoid this interaction with Mike. Is there someone that knows how I could avoid this interaction with Mike and still be convinced? Is there anyone familiar with ZKP? I knew it, nobody. OK, so the thing, and what's the point behind snarks in general and all of these non-interactive proofs, is that we can actually have a common reference. Let's say someone, it wasn't me, we agreed with Mike that he will use a random, let's say, string that is found in the internet, and we all agree on it, to simulate these examples I did, then give me all the results back, and I can verify without interacting with him. This is the trick behind ZK snarks. They use something that actually simulates this random interaction. And as we said before, the ZK snarks, if you don't know what it means, is such a non-interactive argument of knowledge, which is zero knowledge, what we said before. It's non-interactive. This is very important. Another thing that Mike couldn't do with this experiment is that he couldn't transfer my proof. It's only between us. But in DLTs and blockchains, this can't work. We need transferable signatures. We need transferable proofs. That's why this is practical. The main difference from the previous attempts, it enables signatures to be transferred between members. So if we had the common reference string before, then Mike could send his output, his choices, to someone else, and again, he will get this common reference string and can verify, can simulate again the verification process. Also, the nice thing is that it's very short. Back in 2007, I forgot to remind you that in 1985 that this all zero-knowledge proof, let's say, industry started to happen, and there are algorithms proposed. The first paper was rejected a couple of times. Then they won the Gödel Prize, and now the two of the first authors won the Turing Award. So imagine that people don't initially know how this will be applied, but we eventually have some real proofs and some real applications. The fact that the signatures are very short is very important. Before 2013, there was not a solution that the proof can be really short so people can actually use it. Now, it's just 280 bytes, whatever the problem you're going to solve. This was a major discovery, and this changed everything in the zero-knowledge proof world. And argument, what's an argument? As I said before, we're just changing balls here. But an argument is everything you can run on your computer and can result on something. You can prove that something is true without revealing all the inputs. Actually, there are zero-knowledge proofs that you can have inputs. You cannot use inputs. But practically, we use something like a key, like a balance. These are called non-deterministic witnesses or auxiliary values. You will see it in different aspects and different versions in the internet. OK, so what's the complexity behind it? It's really nice. It's amazing that we have this, but it's not so easy to come up with a proof that everyone accepts. You get a program, whatever the program it is, you transform it in a way that you create actually a circuit of logical gates. The thing is that we need thousands or millions of them sometimes, because imagine that even a short program will be eventually a combination of multiple connected gates in order to produce the output. You will need some transformation as well. For example, because let's say we don't support inequality, we have to convert everything to equality. And we have a very simple example here. How can I prove that, for example, someone has age less than 2? What we can do to transform this inequality to an equality. One is by subtracting this number, getting the first bit, which shows if it's positive or negative, and you have an equality. The other thing is you can do x, the age, minus x times x minus 1, x minus 2 equals 0. if x is 0, 1, or 2, then we have an equality, and the outcome will be 0. So we converted the inequality to an equality. So there is a need for some people to convert real programs to these logical gates, which is not so easy. So sometimes you need special stuff that can do this conversion. Then you have this, let's say this is the most technical part, but it's only this slide. You have this circuit, and you have to convert it to something that you can do operations with it. Initially, you convert it to a rank 1 constraint system, as it's called, and imagine it's just 3 vectors. Actually, they are sparse vectors, and they satisfy an equation. We're not going into the details of this equation. Then, again, you need another algorithm, that you create a polynomial from these vectors that actually are dot product operation. And after you go to the arithmetic quadratic program, you go to the elliptic curve encryption using bilinear pairings, and then you have the ZK snark. This is something just to understand that there is a process of almost 5 steps, and that's why it's very complex. OK, it works, but what are the side effects of it? One of the side effects is it uses special elliptic curves. There are no real standardizations for elliptic curves. Even it took years for the actual ECDSA, or now EDDSA, which is not still standard. And we need another type of curves now, which are pairing friendly. But there are attacks on these curves. The problem is it's not standardized. We have to use some other curves that are not really tested in the world for a couple of years. Are we sure that it can work in a matter of, let's say, 3 or 4 years and not another attack will appear? Because every year we have a reduction on the security level they offer. At the moment, for example, there is ZKs, there is 0Ks. They use some curves that practically they provide less than 100 bits of security. But today, the standard is 128. It's true that we can't still break with conventional computers these bits of security, but we have to go to bigger curves. That's one of the problems that concerns us, and we're still doing research if this can be applied to Corda at the moment. Also, this is the bad thing with ZK snarks. We need this trusted setup, the common reference string I referred before. This is the toxic waste of the ZK snarks. Even for ZKs and 0Ks, there was a need for a ceremony between people that will exchange some ideas and some information, and they will come up with a common reference information. This needs to be trusted because they can forge signatures. If, in reality, ZKs and 0Ks didn't follow the process as expected, they can forge signatures. They can spend whatever they like. We don't know if they follow the signature. This is what they claim. I personally believe them, but you don't know. The other thing is that ZK snarks are not post-quantum secure. Quantum computers are coming. We know it. We see the progress already. The last years, it's going faster. And what we can do is just change to another snark, not snark now, it's called ZK Stark protocol, which is not practical. The keys are huge. And the thing is that there is low performance. As you can see on the diagrams on the left, right for you, you will see that to create a proof, it takes 10 to 40 seconds, initially some minutes. Imagine that Eli Ben-Sasson, one of the creators of ZK Snark, said that 128 SAT256 functions will take an hour or so, and for 1 million of gates, programs that are 1 million of gates will take hours. Now we've managed to go even faster, and eventually, I have heard that there are some attempts that minimize this to 1 or 2 seconds. I'm not aware of any. I haven't seen something running in such speed, but that's the truth. And although the proof generation is very slow, the verification is very fast. It's just some milliseconds. And as you can see, regarding the key sizes, conventional cryptography like RSA and elliptic curve crypto, the proof size for the zero knowledge proof is OK, acceptable, but you need 1 gigabyte of params, which is too much. So I just finish with the ZK thing, and let's see why there are some concerns on applying these technologies and why everything can actually break. So there is this algorithm, the evil algorithm, the source algorithm that can actually break factorization and D-log if quantum computers appear. You will need a couple of qubits, call them qubits, and some quantum gates. But it's true that if we manage to go to this level, then there is an easy algorithm to break all of the existing cryptography. That's one of the problems of public blockchains. Imagine that public blockchains are public. There is history. One can break them because everyone has access to them. That's one of the differences between the private and the public blockchains. The estimated risk is about 15% to have an algorithm that will break, let's say, elliptic curve 256 by 200 and 2026, and 50% by 2031. Also, I'm going to this side of the slide. Symmetric encryption, although it's still safe, as I said, RSA and elliptic curves will break. Symmetric encryption, although it's safe, there is an algorithm also called Grover's algorithm that will also need bigger keys, so we're safer. This means that AES 512 or even bigger will be required in the future. And we should, yes, this is the double size. And ZK snark, again, it's based on the elliptic curves. We have to go to something else. However, there is a paper recently from Daniel Bernstein that says we can still stay with RSA, but we need keys of the level of terabytes. Yes, it's possible, but yes, it's terabytes. What's the current state on quantum? Oh, well, we need this amount of qubits, more than 1,000, and surprisingly, RSA is more difficult to break on the quantum world because the keys are bigger. And it's very interesting that there is this difference. At the moment, we have Google announcing that they will build an annealer and quantum annealer with 100 qubits by the end of 2017. I don't think they will manage to do it, but probably 49 or 50, it's possible. The largest number factor is still very small. It's just 200,000. But there is some companies, for example, D-Wave, that they announced a 2,000 qubits processor. And the thing is that they're only focusing on AI problems. It's targeted on machine learning, and it's actually for quantum annealing problems. And as they state, I think they don't have plans to do it for security purposes, to crack algorithms. This is 10,000 times faster than conventional algorithms. There is still some work to be done on error correction. But what can we do? OK, let's say by 2025 or 2030, we have the quantum computer. What's happening with our current infrastructure and transactions? Well, some of the countermeasures we can take is we use hashed keys. Bitcoin does it already, but what it does is just minimizing the window of attack, because eventually you would like to spend the amount, and there is a window that someone that could break faster the elliptic curve key can send a transaction as well, and who knows which will be first. There is also the ZK Stark for zero-knowledge proofs, as I said before, not practical yet. We use Sphinx in Corda. We have support for Sphinx. Corda is already prepared for the quantum apocalypse. We support 5 algorithms. One of them is the Sphinx, which is post-quantum secure. And there is an algorithm for key exchange, like the Diffie-Hellman we have now. It's called New Hope. Google actually tested New Hope combined with some elliptic curve encryption recently. And there are some quantum algorithms. There is some work happening on using quantum encryption and quantum signatures, probably using either optical fibers or satellites. There is some work, significant work being there, and we're expecting the results because I still have some concerns over their application, but they're going on the correct path. So this is the current state for post-quantum and zero-knowledge proofs. Back to Mike.
OK, thank you, Kostas. Yeah, that was pretty good. I'm not even sure I did the balls correctly, but you got the idea. All right, so how is this relevant to Corda and DLT? So there's two ways in which things like Corda and its competitors can use zero-knowledge proofs, right? The first is like the automatic, you don't have to think about it, everything becomes hidden automatically, that's the holy grail, right? And that's kind of what we're aiming for with SGX. I said earlier, you won't have to understand all of how the hardware works. You'll just write your Corda apps and follow the instructions, and everything gets encrypted, and it goes away. So that would be great if we could do that with ZKPs, but that's really hard. That's a long way off. And then there's a second, slightly more practical in the short run approach, which is these sort of ad hoc tactical integrations by experts. And that's more realistically what can be done today if you accept the caveats, which Kostas has done a good job of describing. So these are cases where we take a really important, widely used application, like maybe cache, and we go in and specialized cryptographers apply a zero-knowledge proof to that application, specifically to a small part of that data, and we launch that integration, right? Now, it's for this reason that if you look at the space of DLT frameworks, so Ethereum is interested in this, and Quorum sort of inherits that interest, I think, and that they're partnering with Zerocache. There is one production system, which is Zerocache, which uses this technology, and they run a system that works, and it's slow. If you send a zero-knowledge protected transaction, then you're up to your 40-second time to send money, but it seems to work. But there is a huge catch, which people are not discussing, which is that this only works for cryptocurrency assets, right? Because they did that approach. They had specialized cryptographers who took a very specific application, which was cryptocurrency, and they integrated a custom zero-knowledge proof just for that app. So you lose smart contracts. And Zerocache is, in fact, a modified Bitcoin, and you have two types of transaction and two types of coin in the system. You have the magically protected kind with zero-knowledge proofs, and then you have the ordinary kind, because if you want to do anything fancy, that's the kind you have to use. Right. So, and our working assumption is that that's not going to fly, right? You can't, people come to DLT and they say, we really care about being able to define our own asset types, our own business logic, our own smart contracts. We can't have a situation where normal programmers can no longer write apps. That's not acceptable, right? So that's what we see in the market, and that is a problem. The core issue, which was touched on very briefly by Kostas, I don't know if you noticed it, is called arithmetization. To write a zero-knowledge proof today, a proof demonstrates solutions to systems of algebraic constraints, right, systems of equations. Now, equations, I'm willing to bet no one in this room has ever written a program in the form of pure equations, right? I'm sure of it. I will bet you guys anything. None of you have ever done that, because no one does. That's not how we write programs today. Right? And in fact, it's extremely difficult to express even very trivial business logic, like an if statement, with equations. And this is why simple problems balloon up into millions and millions of equations when you do these transforms that Kostas mentioned. And that's just the first stage to get to the circuits. And then you have the other 5 steps, which are all very slow and expensive as well. Now, totally not realistic to expect non-specialists to write rank 1 constraint systems, because this is what it looks like. This is a part of the Zerocache code. So this is a DSL on top of C++. So those of you who know C++ can probably read this. Well, it looks like ordinary code, so you can probably all read it. But observe, I wonder if I have my laser pointer. Yes. Observe things like this line, witness phi. Well, what does this do? Don't know. Does it matter? If you take it out, does things break? Probably. This is code. This is one part. So this is a small excerpt of the code which loads values into the proof system for proving. It doesn't even do the proof. And all it does is check that the left-hand side of a transaction adds up to the right-hand side, so that you haven't destroyed or lost money. That's all it does. And it takes a long time. And good luck writing this code if you are not, though I can understand parts of this code, I wouldn't trust myself to write it, right? Because I'd probably make a mistake. So zero-knowledge proofs, called moon math for a reason, right? So here's another problem which Kostas did not touch on, but vexes me very much. And I think I may write about this problem soon, because this is a risk for the whole field of cryptography. Cryptography is associated in people's minds with unbreakable, right? People hear the word encrypted and they say, cannot be broken by man nor machine, completely solid. And cryptography has this reputation because it is a very conservative field, because the systems of cryptography we use today are rooted in research that dates from the 1970s and 1980s. And all crypto today is based on the assumed hardness of mathematical problems. We don't know they're hard. We can't prove they're hard. We just suspect, we think they really must be hard because lots of really clever people have spent a lot of time trying to solve it and God, they got nowhere at all. So it must be hard. Unfortunately, these modern branches of cryptography that we're talking about here are not like this, right? They are based on what's called bilinear pairings, which is a new branch of crypto that started around the early 2000s. And one of the problems of this subfield of cryptography is the researchers like to invent new mathematical problems and assume they are hard. And are they really hard? Well, there have been some unfortunate events in the past where cryptographers have published papers and they've said, here is a new mathematical problem. It's really hard, and even better, we have proven it is really hard. We have a security proof that this mathematical problem is genuinely unsolvable. And then in one case, a year later, someone published a solution. So it turns out it's not proven after all. And if you look into how that happened, what you see are, unfortunately, cryptographers often obfuscating the strength of what they are doing, because this allows them to publish papers. These security proofs that they give are based on certain assumptions. The proofs hold if the assumptions hold, and yet these assumptions are getting less and less realistic with time. Ever newer crypto is now being deployed into production without the customary 10 or 20-year wait that has previously preceded deployment of new crypto systems into production. So people are now, and the reason this is happening, of course, is suddenly zero cash means there is a path to money from deploying new cryptography. So we're seeing algorithms being implemented and deployed to production that are only a year old, that have been proposed in PowerPoint presentations, right? The peer review, is it there? Maybe. So these are the risks. And then finally, of course, you've got huge key man risks because this is very, very hard to understand. So if your team gets hit by a bus or, all quits because someone gave them a better paycheck or whatever, you can risk ending up with code that no one can understand. And good luck ever hiring anyone who can tell you what it does or how to fix it with the current state of the technology, right? And it's for these reasons that when this technology was first introduced to the Bitcoin community, I was there in the room in 2012 when the very first presentation by ZKP researchers was given to the cryptocurrency community. It was immediately nicknamed Moon Math because it seems like alien technology, right? That's how complicated it is. Now, I sound down on this, but I'm kind of not. Mankind did reach the moon in the end, right? It took a lot of work, but we put a man on the moon. And this is really hard. It is Moon Math, but right, we will get there in the end. Humanity did that, and we will succeed at this too. But the question is when, and how many people will get blown up along the way? Now, things we need, right, to achieve that holy grail. Right, what we need is a compiler, a special kind of compiler that doesn't compile to machine code. It compiles to equations, algebraic constraints. So you can feed in your existing Java bytecode from your verify functions and your Cord apps, and which converts them to rank 1 constraint systems or one of the other systems of equations which these proof systems use. And the goal here is such that we abstract the difficult bits so that ordinary programmers who are experts in interest rates and derivatives trading and all this stuff can build these systems without having to study 10 years worth or 20 years worth of academic research. And of course, maintain them. Trustworthy initialization. As Kostas mentioned, Zero Cash was initialized by a bunch of people who claim they went through this fascinating ceremony where they bought computers and then smashed them with hammers and things so that the private key material won't leak. But did they go through that? I mean, it sounds like a good ceremony, and they probably did. But if they just got together and pretended they did, and it was all a bit of theater, we would never know. And yet, it would have allowed them to print as much Zero Cash as they like. Now, if in effect it turns out that it's impossible to design a ceremony which completely removes the chance of failure, the chance of funny games, so what you need to do is change the algorithm so there's trustworthy initialization. Post-quantum ZKP, Kostas has talked about that. We need a way to deploy it into a live network, of course, because by the time this technology becomes usable for this holy grail approach, we will already, hopefully, unless we fail very badly, we will hopefully have live production networks running with SGX and running with other technologies that we need to deploy into. So we need a way of incrementally deploying this technology. Right? Yes, it's not normal that I ask for people to innovate less fast. Usually that's a good thing to invent new things. But in this case, of course, the problem is that these algorithms are now changing almost every year. Right? Almost every 4 to 6 months, a new academic paper comes out with big improvements to this technology, which is awesome. But what does it mean? It means that all the peer review of the previous stuff is somewhat invalidated, right? We go back to square one when it comes to testing a lot of this maths, because it's all changed. And because the peer review of the maths would be so nice, because that is where all of the trust in cryptography comes from, we need at some point for these algorithms to stabilize so we know what is actually being checked and to some extent who has checked it, and we can check if there are mistakes in these maths, because there have been mistakes in zero-knowledge proof algorithms that have been published in court, right, but only a long time after the papers were published. And we assert, well, really, I suppose, I assert that these things are not really Corda-specific. These concerns are actually general for all DLT systems. We can't ask you to learn the zero-knowledge proof technology in its current state, right? People like myself and Kostas, we read these papers so that we know what's happening in this space, but it's not reasonable to ask people to learn this stuff when it is so hard, right? The apps are hard enough to write already, so until we have a working abstraction that makes it easy, like we are building for SGX, it's very difficult to ask people to really get a grip on this. Unfortunately, if you look at, for example, what Ethereum is doing and so on, they sort of gloss over this. They say, we'll add an instruction to the EVM that checks a zero-knowledge proof, but you're on your own if you want to actually make one and use it. Well, it's OK for experimentation, I guess, but that's not going to help us in the short to medium term. OK, so again, I don't want to sound too negative on this stuff, right? This is a really, really cool branch of maths, very powerful, very interesting. This stuff will be in our futures, right? And I want to see them succeed. I really do, right? This stuff should succeed because this will make society better when we can eliminate trust from things with maths. And in one day, for some things that we will be using SGX for, this could be used instead or on top of. Not everything, right? Secure hardware is more general than zero-knowledge proofs, so you can do some things with it, but not everything. And although we haven't gone into them in this talk, we do actually have fairly detailed plans about how to do some of this work, right? We've done some design thinking around it. We don't plan, it's not on our roadmap, right? We don't plan on implementing it because we're still waiting for research to resolve some of these other issues. All that said, what I've been talking about here is the holy grail of all general, automatic privacy of transactions. There may still be, right, ad hoc specific, contract-specific cases where the integrations make sense to think about, like a cache-specific zero-knowledge proof, securities-specific zero-knowledge proof, or whatever. Okay? So that's our thinking on zero-knowledge proofs, and I hope you have a better understanding of this technology now, because you'll certainly be reading about it from other players in the DLT space. And that's the talk. So any questions?
I think we have about 5 minutes for questions, just because we on the optimistic clock, we got 5 minutes. We'll run with that.
All right.
So we don't hold you back from drinks.
Hi. There's been this maybe cryptic and strangely named cryptocurrency proposal / prototype called Mimblewimble. I don't know if you've heard about it. If you did, I wonder how does it kind of look in this context in terms of security of the crypto and its quantum security?
Yes, I have. That's the one written by the guy who uses Voldemort's name, isn't it? Yes. I prefer the name Satoshi, to be honest. Mimblewimble, I'm aware of it exists. I haven't really looked at it. I can't answer the detailed level of questions you're asking about it, I'm afraid. Probably isn't post-quantum secure. So, as Kostas mentioned, all of the existing techniques really today are built on top of elliptic curve cryptography, which is not. Therefore, I would be very surprised if it is. This is something that people are starting to think about now, but schemes up until really this year probably wouldn't have focused on it much.
Another question? Yeah.
Just quickly, is Monero using zero-knowledge proofs in their protocol?
Monero uses ring signatures. So that would be an example of a sort of non-generic, what I call, calling them ad hoc integrations makes it sound a bit bad. There are techniques, that's a technique that can be applied very specifically to that case where they've integrated it for cryptocurrency transactions. That's the sort of thing where we may well consider in future, but it would not help the vast majority of people building apps on top of the platform, right? It would only be applicable to a single contract, probably cash. Yeah.
And probably one more question. All right, excellent.
Okay, we're done.
Thanks a lot, guys.
Great, thank you.